Welcome back, everyone. So this session is going to have two talks, and the first of the talks is by Gregory Fiete, and this is going to be about nonlinear optics, probing and control of magnetic and electronic quantum geometry.
Thank you very much, Sanjeev. It's a pleasure to be here, an especially bigger pleasure than usual, because I have an intimate connection to India. My wife is from India. And we have two wonderful children, so we come here often, but this is actually my first trip to India by myself. My wife and kids are actually at a family wedding, which is being held in the United Kingdom. So they're at a family event outside of India, and I'm in a scientific event in India. So thank you to the organizers for giving me a chance to speak here and visit this wonderful country. So my talk is about nonlinear optical probing and control of magnetic and electronic quantum geometry. So there's a selection of topics that I'll cover here. All of them involve light-matter interaction. In some situations, the light is going to be used to change the matter and to push it in some new out-of-equilibrium situation. And in other cases, we're going to use the light to probe the matter and try to get information about the quantum properties, such as the quantum geometry, things related to the quantum metric and Berry curvature. So an outline of the talk is the following. I'll give some motivation, which comes from both theoretical considerations, such as the diversity of the sort of knobs that you have at hand when you're using light interacting with material, as well as some experimental examples that I think are quite interesting for how light can change the properties of a material. And then I'll go through a number of different topics that we've looked at kind of under this broader umbrella. The first one I'll cover is a way that you can tune the effective twist angle using a Floquet drive, which is a periodic drive which would originate in a laser that's incident on a material. Then I'll switch to talk a little bit about nonlinear phononics. And this is where you tune the light frequency to resonantly excite certain phonons, vibrational modes of the crystal, but with a very high intensity light, so that you push the displacements of the phonons beyond a harmonic regime. So you have nonlinear effects, and you can use the excitation of one phonon to couple to another phonon, and it turns out that in some situations, that allows you to control the magnetism and even the electronic band topology in materials. And I'll give two examples that we looked at here, which are in thin film form, bilayers. Then I'll switch from using light to change the properties of a material to using light to probe the properties of a material. So we'll look at the nonlinear optical responses and essentially the remaining topics. So we'll look at Weyl systems, we'll look at superconductors, and we'll look at ABC rhombohedral graphene. And see what we can learn about the nonlinear optical response of topology and other more general quantum geometric features of the band structure. And feel free to interrupt me with questions at any time. Okay, so first, by way of motivation. So this is probably the main reason why I have been spending the last few years looking at how lasers can be used to tune materials. Mainly, it's because there's so many parameters that you can control. So before I started looking at light-driven materials, I was very interested in ways that you can change material properties by applying strain or some kind of a substrate to the material to deform it in some way, or maybe electric fields or magnetic fields or pressure. I was interested in how can you take a material, push it in some new way, and then get some new phenomena out of it, maybe a new type of order, or maybe enhance the strength of an order that was desirable, like some kind of superconductivity or something of that sort. But then eventually I came to the point that, well, if I give up the equilibrium constraint, so if I accept that there's certain challenges being out of equilibrium, but there are certain advantages of being out of equilibrium, then actually you can get a lot more out of a material in terms of like the sort of phenomena that it might exhibit. So light is particularly interesting and very flexible. So you can change the polarization of light. So you can have linearly polarized light, you could have circularly polarized light, You can have a linear combination of the two, some elliptically polarized light, but these linear and circular regimes kind of represent two extremes. So linearly polarized light will preserve time reversal symmetry in the system, whereas a circular polarized light, which has a certain helicity associated with it, when it's incident on the material, then the combined material plus the light will always have broken time reversal symmetry. So even if the material did not have broken time reversal symmetry in the absence of the light, once the light is there incident on the material, the combined system is broken time reversal symmetry, and that's going to allow certain sort of responses that require broken time reversal symmetry for the system. You can change the frequency of the light, so you can selectively couple to different degrees of freedom by choosing the resonant conditions, either with electrons or with phonons or with magnons or whatever it might be that you're interested in. I should emphasize that light doesn't need a charged particle to couple to. Light will couple to magnons, and they're electrically neutral. So you actually have quite a wide range of excitations that you can get access to with light. You can change the intensity of the light, sometimes called the fluence. It's kind of the amount of energy per unit time that the light is carrying. So your frequency is fixed by the laser, but you can put more energy into it and get more light out, more photons of the same frequency, and that intensity is an important knob. So for a fixed frequency of light, as you sweep the intensity of the light, you can get very different responses. So when I talk about the nonlinear phononics, if the intensity of the light is not sufficiently large, then you won't push the phonons into an anharmonic regime. You'll remain in that harmonic regime. But beyond some critical intensity of the light, then you start to see anharmonic effects. And so the response of the material can vary dramatically depending on how intense the light is that you're shining. The angle of incidence relative to the material orientation, there are matrix elements and how the light's going to couple to phonon or electronic degrees of freedom. And by changing the relative angle of the incident light with the crystallographic directions, then you basically can play with matrix elements and give different material responses, all other things being held equal. Sort of a new frontier which is emerging in condensed matter physics on the experimental side is shaping the pulse of the light. So most of the experiments that are done with light are done in a pulsed form. Like you have your laser produce pulses of light, which have some time delay in between them, and you can change the frequency composition of that pulse. You can chirp it, or you can shape it in various ways. This sort of strategy is used in quantum chemistry to try to influence reaction rates of chemicals, but so far not so much used in condensed matter physics, partly because there aren't very many theory predictions saying that if you shape your light pulse in such and such a way, you'll get an interesting response. So that's not a topic that I'm talking about today, but it's kind of an open question. How do you use this degree of freedom with a laser shaping the pulse in order to get some kind of interesting response out of the material? And then you can even use more than one laser to drive a material. So you can have one laser of a given frequency and intensity, and then apply a second laser to get kind of a response on top of a response. And that is another very interesting direction that so far is not that much explored. There are a few experiments that I'm aware of, but that's, again, another frontier. So to give you a sense of the sort of things that can happen, one of the simplest ways that you can take a system out of equilibrium that has a time dependence in it is to have a strict periodic time dependence. So probably everyone in the room is familiar with Bloch's theorem for crystals, where because of the broken translational invariance of a crystalline lattice, you no longer have a continuous translational symmetry in free space, which gives you momentum conservation. Now you just have a discrete translational symmetry, so you retain a weakened version of momentum conservation. You have quasi-momentum conservation, which gives rise to a Buron zone. So you have a certain finite range of wave vectors where all of the information of the spectrum and the wave functions are contained. So that's not a property of the real space variable. It's just a property of the periodicity of the Hamiltonian. So in quantum mechanics, a time-independent Hamiltonian is what's responsible for conservation of energy because it has a time translational invariance. So if you break the time translational invariance from continuous, constant Hamiltonian, to a time periodic one, then you have an analog of Bloch's theorem, but for time. So you have a quasi-energy zone now, and you have energy which is only conserved multiple some thing which is the analog of the reciprocal lattice vectors, which in this case are like integer multiples of the frequency of the drive times Planck's constant. And so what's produced then, you can have an extended zone scheme in real space for Bloch's theorem, and you have an extended zone scheme in energy space for a Floquet system. So this very nice experiment from Nugetics group at MIT illustrates that through a time-resolved, angle-resolved photoemission spectroscopy. So you send in light, you eject electrons, you collect these electrons with energy and momentum resolution, and you can reconstruct the band structure where they came from inside the material. And this particular material, bismuth selenide, is ideal for seeing these Floquet states. So seeing these copies, which are the energy equivalent of the extended zone scheme. We have an extended zone scheme in space. So this material is a well-known topological insulator. There's a bulk band gap, but on the surface, you have these famous Dirac cones. So in this experiment, he drove the system with a frequency of light which was below the bulk gap to avoid any kind of resonant excitations in the bulk of the material. And therefore, you can only create electronic excitations in the surface states. And so those surface states are the ones that primarily respond to the light. And so what's imaged here using this time-resolved photoemission is basically electrons are populating these extended energy zones when a pulse of light is incident. So you should think of each of these slices as corresponding to a time slice of this pulse. Over here, the pulse is not present, and over here, the pulse is not present, and you see a single Dirac cone. But near the middle of the pulse, where if you look a little bit to your past, you look a little bit into your future, then you see basically something which is, to a good approximation, periodic in time, which is a slight intensity variation. And so the system basically sees a Floquet drive near the center of the pulse, and that's what is illustrated in this data, which is showing basically Dirac cones which are stacked on each other in energy with a spacing that is equal to Planck's constant times the frequency of the light that you're driving it with. So these are the Floquet states. And so in this example, the light has been used to fundamentally change the material. Another example is graphene. So graphene on its own has time reversal symmetry preserved, but if you shine circularly polarized light on it, then you can break the time reversal symmetry, and that opens up the possibility to have a kind of light-induced quantum anomalous Hall state or Chern insulator. So it's kind of a Floquet Chern insulator. And this experiment showed some indications that that may be what's happening. So as you increase the intensity of the light, the Hall conductance approaches what would be the ideal equilibrium value for a Chern insulator, which is 2e squared over h. And then this is consistent with a band structure reorganization coming from the photons addressing the electronic band structure. The interpretation of this experiment is probably a bit more complicated than is proposed here, but it gives you a sense of the idea that you can fundamentally change the properties of the experiment. This one actually was a tour de force, and the measurement was a transport measurement, as opposed to the one before, which is kind of a photo measurement, where you're basically ejecting electrons using photons. Here you have to do transport while illuminating it with a laser. It's much more difficult because you have to have the laser on for a longer period of time, and that leads to heating effects, which tend to complicate things. So coming to the theme of the conference, engineering of 2D materials. So in this first project from the group that I want to describe, we can look at kind of the hydrogen atom of twisted materials, which is bilayer graphene around the magic angle. And so the extra bit that I want to add here is light. So we can take bilayer graphene around the magic angle, shine light on the system, and ask, how do these flat bands near the Fermi level change? So an important detail is, what is the electric and magnetic field directions of the light pulse relative to the direction of the light? So if we have light which is normally incident, then basically Poynting's vector is perpendicular to the plane. So it means that the electric and magnetic fields are in the plane of the material. So it's only going to couple to the electronic motions that are in the plane, not between the plane. So for those who have seen a Hamiltonian like this for bilayer graphene, you know that the band structure flattening is intimately related to these off-diagonal elements, which is related to hopping and coupling between the planes of graphene. So we actually need a way to have the light, couple predominantly to the perpendicular direction to the layer, not the in-plane direction. And that can be achieved by using a waveguide. So a waveguide produces a parallel component of the vector potential, which then couples into the interplane hopping, and that will lead to a renormalization of those flat bands, which is equivalent to changing the twist angle. So depending on the frequency of the light that you choose, whether it's like a larger frequency light or a lower frequency light, you can actually decrease the bandwidth or increase the bandwidth of these flat bands around the Fermi level just by choosing the right sort of light. So it's equivalent to taking your system and making very small angle twists. So in principle, you could have a laser with a tunable light, a tunable frequency, and tune the frequency, and effectively for a physical twist angle, which is not changing, you can modify the band structure as if you were actually changing that twist angle. Okay, so now staying with the theme of using light to change material properties, now I want to switch from light, which is coupled to the electronic degrees of freedom, to light, which is coupled to the lattice degrees of freedom, photon. So our first example is going to be this system chromium triiodide, which in bilayer form is an antiferromagnet. So you have very strong polarization of the spins within one of the two layers of the bilayer. So it's ferromagnetic within a layer, but the coupling between the layers is antiferromagnetic. So overall, the system has a net zero moment. But in equilibrium experiments, say applying a perpendicular magnetic field, you can change the system from its equilibrium antiferromagnetic configuration to a polarized ferromagnetic configuration without a very large field, just around a Tesla. So this is telling you that the interlayer magnetic exchange is not a very large energy scale because the field doesn't need to be very large in order to fully polarize it. You can also change the antiferromagnetic configuration to ferromagnetic one by gating the system or by applying pressure. So a significant amount of pressure, something on the order of 2.7 gigapascals, is going to achieve the same thing. It's going to fully polarize the state. So these equilibrium methods of changing the magnetic order in this bilayer chromium triiodide gave us hints that we might be able to do this via an alternate means, via light. And so that was the question that we asked here. So can we change this antiferromagnetic configuration to a ferromagnetic configuration using light? So you might say, well, why do I need a fourth way? I can already do it three ways. Well, none of these are very fast. Light, we can turn it on quickly, turn it off quickly. So we could basically have a switchable system. So just with the right sort of laser light, we could switch in a tunable and reversible way between these two configurations with ultra-fast tunability. And this is also just kind of a first test case. As I tried to emphasize earlier on, there's so many flexible knobs that you have with light. So this is just kind of a test case for what we might be able to do with light. There may be other things that we could achieve with light, other sort of order changes or intrinsic material properties that could be changed that cannot be achieved with external magnetic field, electric fields, or pressure. So the idea is to use nonlinear phononics. So if you have a system with inversion symmetry, then the phonons nicely break up into even and odd types. There are infrared active modes, which directly couple to light, and there are Raman modes, which only couple second order to light. And it turns out that these Raman modes are the ones whose structural changes associated with them are more natural for changing the electronic properties. But these IR active modes, which couple directly to the light, are the ones that are most naturally excited by light of low frequency, sort of in the infrared. So the idea is that these IR modes typically are much higher in energy than the Raman modes. So we have a situation where there's a separation of timescales. The IR modes are fast modes compared to the slow Raman modes. So we could time average over these IR active modes and ask about the effect of the time averaged IR active modes on these Raman modes. And the effect, if you have an intense light and nonlinear coupling between them, is to shift the equilibrium oscillation position of the Raman modes. So there's a transient structural change in the crystal, and we know that electronic properties are intimately linked with the crystal structure. So if we change the crystal structure, we have a lot of possibility for changing the electronic and magnetic properties as well. So we used that strategy in a theoretical study of this chromium triiodide structure. There's two components to it. So one component is to use a symmetry analysis, essentially from group theory, to identify what is the effective potential associated with the distortions of the lattice. So capital Q here, these are distortion modes of the lattice. So IR is for infrared, R is for Raman. So there are harmonic pieces that would come if the displacements were sufficiently small. There are some unknown frequencies associated with the IR modes and Raman modes. And then there are nonlinear terms. So there's nonlinear terms to the Raman modes. There's couplings between the IR modes and the Raman modes. And notice that this is the square of the IR mode, which couples to the Raman mode. So if you time average some kind of periodic function squared, then it's going to have a non-zero value. So the square is very important. That's what's going to lead to a shift in the equilibrium position of this, because I'll now have a quadratic Hamiltonian with a linear piece, and you can just rewrite the Hamiltonian. You'll see that there's just a shift in the equilibrium, which will be related to this gamma I. And then there are other nonlinear terms, and these coefficients, delta, epsilon, zeta, need to be fit from first principles calculations. And so we had collaborators who do first principles theory, compute these numbers for us, including these frequencies. So these are the results of the frequencies, and these other numbers can be obtained as well from first principles. So we have very material specific calculation. So symmetry gives us the form. First principles gives us the numbers of this effective potential. And then the question is, how do we couple to these various zone center, these are Q equals 0 modes, because the light wavelength is very long compared to the lattice. So the ones up here, which are kind of darker blue, those are the IR modes. And you can also, from first principles, calculate an effective charge, telling you how strongly they couple to an incident light source. And then these nonlinear terms here will tell you how strongly these IR modes couple to the Raman modes of lowest energy, which are down here in blue. So it turns out that if you analyze the dynamics of this, the greater the separation in energy between the IR mode and the Raman mode, then all other things being equal, the greater the response of the Raman mode will be. And it turns out that this particular Raman mode here, which is a shearing mode in between the two layers of chromium triiodide, is going to produce the largest response. So what's shown here is these three Raman modes, which are lowest in energy, and how large the displacement from the equilibrium position is when they're driven by an electric field coming from the laser driving the phonons. So this one in purple is the greatest one. That's this shear mode between the two layers. Then we have a Hamiltonian, which has been characterized by neutron scattering. So we know these coupling constants. We can look at how the coupling constants between the two layers, the interlayer coupling constants, change as a function of the displacement of this shear mode. And the important figure is here in the lower left. There's a black dotted line, which is horizontal with 0 energy for this interlayer exchange. And that's actually crossed. So you change the sign of the interlayer magnetic interaction, which is a change from the antiferromagnetic to the ferromagnetic. So basically, this strategy of driving the IR active phonons, which then nonlinearly couple to the Raman active, producing the shear mode, has the effect of switching the sign of the interlayer magnetic coupling. And so the system goes from an antiferromagnetic to a full ferromagnetic change. So we also looked at this material, which is quite interesting in its own right. I think maybe last week it was discussed a bit before I arrived. So MBT and also MST, bismuth and antimony. The physics here is very similar. We looked at a bilayer system. There's some details which are a little bit different in how the IR modes are coupled to the Raman modes. But the strategy is basically the same. You use group theory, symmetry analysis to determine the effective potential, first principles calculations, determine the frequencies and the coupling constants, and then you ask which particular modes respond the most to a laser drive. And in this case, it's not a shear mode, but a breathing mode. So you end up changing the interlayer separation, and that's the one which has the most dramatic effect on the interlayer magnetic exchange. And so we get the same sort of effect here, that the interlayer exchange can be changed in sign. So we can induce a ferromagnetic transition in this otherwise antiferromagnetic state. Again, it has ferromagnetism within the planes, very similar to chromium triiodide. And we looked at disorder, anti-site disorder, which is also typically prevalent in these materials. And it turns out that it tends to help the situation in the sense that you can get a sign change in the exchange constants with a weaker intensity of the electric field that you're driving the system with. And one additional ingredient that comes along for MBT that we did not have for chromium triiodide is that there's a topological transition in the bands. So this system in equilibrium has interesting physics associated with the parity of the number of layers, whether it's even or odd. So odd layer systems have finite Chern number, even layer systems generally don't. Here we have even numbers of layers, bilayers, but when we change the system from antiferromagnetic to ferromagnetic, we end up effectively making it odd layer-like, in that there's a finite Chern number that appears that you can see via a band inversion around the gamma point. Okay, so that was phonons. I want to advertise another work that I was involved with, a collaboration with Swati Chowdhury, who's sitting here. She's going to talk on Thursday about phonons responding to magnetic fields. So a very large phonon Zeeman effect, which is appearing in several different materials that she'll discuss and highlight. So I encourage everyone to look at this talk. So now I'm switching gears from using light to change the material properties to using light to explore the material properties, in particular, using light as a probe of quantum geometry. So I think, again, last week before I arrived, some of this was discussed, but just to make sure the fundamental concepts are there, studies of topology over the last 20 years or so have been very focused on the Berry curvature, because it's integral over the Buron zone, gives you the Chern number, and many of our responses of topological states are intimately related to Chern numbers in some way. Quantum Hall effect, quantum anomalous Hall effect, crystalline topological insulators have a mirror Chern number. You can integrate the Berry curvature around nodal points of a Weil system and see that it's quantized to give you the nodal charges, etc. But there's another piece to this more general object, this quantum geometric tensor, which is known as the quantum metric. And so this quantum metric, one can ask the question, well, what are its signatures in experiment? Is there any kind of analog of quantized response that originates in this quantum metric? It's still very much an ongoing question in research. The short answer is that, at least to the best of my knowledge, there aren't nearly as clean of proposals for how you can see some quantized response in this from this quantum metric, or even clear signatures of the quantum metric. It's often mixed up with other things, which is part of the story that I'm telling here. But in any case, the Weil systems are among the best candidates for seeing signatures of this quantum metric. So we're going to focus on the bulk photogalvanic effects, which is the situation where we're shining a finite frequency laser on a material. The second order response where you have two electric fields, one at frequency omega, the other at frequency minus omega, summed together to give you a DC current response in the system, which requires broken inversion symmetry. So the current knows which direction to go. So you shine light on a material, you generate a current, and we're interested in what is the relationship between the current, more specifically the current density that's produced, and the light that we're shining on the system. And so these photocurrents reveal geometric structure of the bands, and there's shift current and injection current components, which are very important in studying this. So, brief reminder of Weyl systems. You have nodal points, which are twofold degenerate in momentum space. These nodal points project onto the surface to make these well-known Fermi arcs that you can see in photo emission. We don't need anything about the surface states. For this talk, we just need the bulk states. And what's important is that these cones can be tilted. So they're not necessarily symmetric with respect to this gray plane. They can be tilted with respect to that. And if you tilt them so far that they actually tilt through the plane, then the Weyl point is changed to a different type. So we have so-called type 1 and type 2 Weyl points. In addition, there is a charge, a topological charge associated with the nodal point, which can take different values, 1, 2, 3, or 4 in particular. So there's both the tilt and the charge. And what we're interested in exploring is, what are the signatures of the tilts and charge in experiment. So one thing that has drawn our attention in particular, and those that are interested in geometric responses, is that in this ideal situation where you have one Weyl node which is above the Fermi level and the other Weyl node which is buried below the Fermi level, which requires breaking of mirror symmetries and inversion symmetries to create this energy imbalance between the Weyl nodes. They must always come in pairs. So if you isolate the response to circularly polarized light from one Weyl node, you end up getting something which is proportional to the light intensity and the chiral charge of the Weyl node. And so this produces a quantized response in a second order response function. So Chern numbers is a first order response. There are fewer known second order responses that are quantized. And so in this ideal situation of just a single exposed Weyl point, you get this quantized response. Theoretically, and then here's an experiment which tried to see if they actually observe that, and they see something which is kind of close to quantized. It looks like it would like to have a plateau here. It doesn't look very beautiful if you've seen quantum Hall plateaus, but still it looks like it's trying to be quantized, so to speak. So one question that you can ask is, well, why isn't it quantized? What are the dominant effects? Is there disorder in the system? Are there electron-electron interactions? What's responsible for this? So we looked at this question from the point of view of a simple perspective. So we asked, how much of that quantization is restricted to that low energy model? So basically, we wanted to look at a comparison between effective low energy theories of nonlinear responses and more complete band theories that have a full band structure, and ask what the differences were. So first, how is the quantum geometry present in the response? So this is the DC response. We have frequencies at two different values that are equal and opposite, and this produces a DC response, which is the sum of these shifts and injection currents that I mentioned. These shift and injection currents are integrals over K-space and Fermi occupation factors, and there are these little r's here. The little r's are related to quantities that are momentum space derivatives of block functions. So there's connections between a band M and a band N, and then there are connections within a given band, and these are the pieces, the components of both the Berry curvature and the quantum metric, and so they appear in these formulas which are embedded here. So there's integrations over density of state sort of quantities, integrations over quantum geometric sort of features. So basically, this is all folded in to some final response. And so we worked out for this effective low energy Hamiltonian of charge n equals 1, 2, and 3 for the nodal point, that's the topological charge, with chirality given by this expression. U is the tilt of these Weil points, and here is appearing as the exponent of the off-diagonal elements, telling us about the magnitude of the charge. And you need to break certain symmetries in order to get non-zero responses in these various components of the second order tensor. The key thing here is this expression, that if you sum over a particular combination of the injection current conductivities divided through by some non-universal value such as the relaxation time, then you get a universal result. And so one can check this numerically. Essentially, this is the sort of thing to look for. This is the sum of all of those. You see perfect quantization. And the important point that I want to emphasize in these figures is the comparison and contrast between three different approximations. So one is the low energy theory that I showed you around that Weil nodal point. Another is a full tight binding model for which that theory is the low energy theory. And then the green is corrections, leading order corrections added on to the low energy theory that bring you a little bit closer to the tight binding model. And so what I think is particularly dramatic here is that if you look at the orange and the green, which is the full theory, tight binding, and just the low energy corrections to that idealized Weil point, they basically lie right on top of each other. So the first corrections actually give you very significant agreement with the full band structure. So that's potentially very useful in making comparison with experiment. So the second message here is that if you have more than just the two bands, it makes a big difference. So having a four-band model instead of a two-band model, where the four-band model has the same low energy theory around the Weil points, actually completely destroys the quantization. So there's a parameter here, delta, which is telling you how separated the two low energy bands are from the two higher energy bands. And the bigger a delta is, the closer you get to quantization, but you still remain away from it. So having just an extra pair of bands away from those low energy bands basically destroys the quantization. So even in the absence of interaction effects or disorder effects, you already don't expect to have quantized response in the system. That quantization is a strict artifact of that low energy theory of just two bands. So we also have results for n equals to 4 that I won't spend too much time on in the interest of the other things. But we have exact results here. This is new for the literature. And again, if it's just charge 4 for two-band model, you get perfect quantization. So that perfect quantization is an artifact of having two bands, and it's independent of the topological charge at that Weil point. So summary here, that the quantization of injection current reveals the quantum geometry, but that quantization does not survive beyond the two bands. We can use the results that we have for the shift in injection currents with light that's incident in various directions to infer the topological charge of the Weil points, the tilt, and the chemical potential, which is particularly advantageous for some materials which may not have good photoemission characteristics. So photoemission requires very clean surfaces and some other constraints on the material. Optical conductivities and these sort of experiments, these currents are easier from the point of view of they're more applicable to a broader class of materials, so you can still get photoemission-like information using this strategy. Right, so those are the key points there. So still staying with the theme of nonlinear responses probing materials, I want to switch now from Weil semimetals to this topological or candidate topological superconductor. So we heard about these TMDs, particularly the 1T type and the 2H type. This 4HB is a much rarer compound, at least in terms of publications. It can still be grown. it's alternating layers of the 1H and 1T. So it's also a superconductor at low temperatures, a collaboration that I was involved with, focused within the Weizmann Institute, looked at scanning tunneling microscopy from an STM of this material. And as you go from a 1H to a 1T step, then you see that there appears in the spectroscopy to be an edge mode, which is gapless. So it looks kind of like a boundary mode. If there's topological superconductivity involved, you might think, oh, this is a Majorana mode along the boundary, because it decays into the bulk with the length scale that's set by the coherence length of the superconductor. So an important question here is this a topological mode? So it looks like it in STM. So we asked the question, well, does nonlinear optical conductivity shed any light on this? No pun intended. So we have a Hamiltonian, which was an outgrowth of that collaboration. So this is characterized in terms of the relevant orbitals that are involved around the Fermi level. Various parameters of the non-interacting part of the problem are characterized by density functional theory, so it has material realism. And so you can ask, what is the phase of the superconductor? It involves basically two types of pairing on site, which are very important. There's a kind of S-wave pairing, if you will, between same orbitals but different spin. And then there's a pairing between same spin but different orbitals. So it's kind of S-like and P-like. So it's a mixed parity superconductor. And that's very important. There's spin-orbit coupling in the material, which destroys the spin rotational invariance. And then this is the phase diagram. So this axis is a ratio, basically, of the triplet to singlet pairing. And then the vertical axis alpha, this is the spin-orbit coupling that's present in the material. And tuning through these two parameters, you have three phases of the superconductor. You have a trivial superconductor, a nodal superconductor, and a time reversal invariant topological superconductor, or TRITOPS for short. So as a function of these parameters, then this is what the band structure looks like. And the pairing, the sign of the pairing is coded here, with the blue being opposite the orange, so +1 or -1. So you can see that as you change, so you're moving along this axis, you're changing the pairing around the gamma point. So that's the transition from trivial to nodal to topological. And the question is, can you see anything in optical conductivity? And you do in second order. So this is the main result, which is color-coded here. So basically, if you're in this orange phase approaching this boundary, then you'll see some kind of divergence like this. Here, you'll see a divergence like this. Near this boundary, a divergence like that. And if you're in the trivial side, near that boundary, you'll see something which looks like this. So the shapes of these second-order optical conductivities with frequency are then indicative of which phase you're in. So you can do an experiment, look at these sort of shapes with frequency, and see that whether or not you get it. And so this is the actual calculation for the model. And if you look by eye, you can recognize that there's certain features there depending on where you are in the phase diagram. So in the final bit of the talk, because I think I'm just about out of time, we looked at the nonlinear optical responsive rhombohedral trilayer graphene. And we saw a similar sort of thing. So there was a band transition in the system, which led to a sign change in the optical conductivity around a particular frequency. And our objective here was to see what can we say about the quantum geometry of the band structure. So in the previous example, we can see topological properties of the band structure. Here, we wanted to see more generally what can we learn about the quantum geometry, the quantum metric, the Berry curvature, of the band structure where there are sign changes in the optical conductivity. And unfortunately, there's not a clear connection that we could discern. So there's a lot of convolution of joint densities of states, matrix elements between bands, et cetera. So the picture is rather complicated in the details, but the result that we were seeking to find, which is that we can identify hopefully even momentum resolved information about quantum metric by looking at sign changes in the optical conductivity, we weren't able to reach that conclusion in this particular. So we have seen in the beginning that we could tune the effective twist angle of 2D materials. Wasn't specific to graphene, that's the example I gave, but it works for TMDs as well, by using light that's emanating from a waveguide, which gives a longitudinal component to the vector potential. We used nonlinear phononics to change the magnetic order in bilayer systems, and in the case of manganese bismuth telluride and manganese bismuth antimony telluride, we could also change the electronic band structure. We looked at the nonlinear optical responses of various systems, including Weil points, and we saw that we could determine a lot of information about them, like their charge, their tilt, etc. And then we could use nonlinear optical responses to help diagnose superconducting phases, whether they're topological. And then we made an attempt to try to get direct access to the quantum metric via the nonlinear optical response as well, but we learned that it's generally not an easy task. So I will stop there, and I'm happy to take any questions.
Thank you, Gregory. So we have time for a few quick questions.
Well, so that's a good question. So what sets the time scale for which you have this transient crystal structure change? Is it the pulse time that it's spending in the material or something else? It's the phonon lifetime of the IR mode. So as long as that IR mode remains excited, and it's going to decay, but basically that's going to set the time scale. Because as long as that IR mode is oscillating, whatever its lifetime may be, then you're going to have that transient structure change. Yeah.
Wish.
Greg?
Yep.
Yeah, thanks for a very nice talk, like a clear talk. Two comments. One is the mechanism of photon-induced ferroelectricity is very similar to what you talked about on the nonlinear phononics.
Yes.
Okay, except for the fact instead of Raman, you can also have an IR active mode, which can.
Yeah, they're beautiful experiments on STO. Maybe that's what you're thinking of. Yeah.
The second comment is on the quantum geometric metric that you introduced, and that the trace of that metric gives the localization length square.
Mm-hmm.
Okay, and that's basically the physical length scale of the electronic system, which is the length scale governing density matrix of electrons.
Yes. Okay.
Yeah.
Yeah. No, I agree. There are certain things that there's bounds in the trace, integral of the trace related to Chern number and so on. So yeah, there's various relations there. So, I mean, we're aware of those, but we were trying to we wanted to get access to quantum metric ideally. So Berry curvature, in some ways you can get some local momentum information about it because like, if you think about systems that have like Valley selective, optical excitation or something like this, then in a Dirac-like system, which is weakly gapped, then the Berry curvature is concentrated momentum space around those Dirac points. So we were hoping for an analog of that here. Yeah.
No,
but yeah, thank you for the
trace is
comments.
measurable.
Yes, yes. Yeah.
So very nice talk. I have a question on the first part. So this tuning the twist angle by light.
Yeah.
Usually light would affect the whole system that you have. So how would you selectively, so in principle, but you need to be selective for one part of the system in order to induce rotation.
Yeah, well, right. So, the light is going to couple basically in this way. So, electrons which are moving from some position Ri to Rj are going to feel this vector potential via this sort of coupling here. So the vector potential which is produced just outside the waveguide is in the emanating direction out of the waveguide. So it's all in the z direction. So it's just coupling then to the interlayer piece. And the piece which is in plane, then we've eliminated the vector potential there. So we basically arranged the situation with this waveguide so that it's just coupling there. So the only way that light is affecting the material is on these interlayer hoppings. Is that answering your question? I mean, there's heating effects as well. I don't know if that's what you're worried about, but yeah.
Okay, let's thank Gregory again for this wonderful talk. And we move on to the next talk.